In this lecture, we look in some depth into various properties of Poisson processes. These properties would be quite hard to study if one were to proceed just analytically by manipulating formulas. However, by using memorylessness and our intuitive understanding of what the Poisson process really is, they become quite simple, and mathematical manipulations can be avoided almost entirely. We will start by arguing that the sum of independent Poisson random variables is Poisson. But we will then establish the much stronger statement that if we merge two independent Poisson processes, we again obtain a Poisson process. We will see that we can exploit this fact to solve some problems that would be quite difficult otherwise. Once more, intuitive reasoning is the key. Finally, we will spend some time discussing a phenomenon that goes under the name of random incidence. A Poisson process has been running. You show up at a certain time. You look at the size of the interarrival interval during which you show up. It turns out that this interarrival interval that you get to observe is not a typical one. It tends to be larger than the typical interarrival interval. We will understand what exactly is going on, build some intuition, and realize that this is a general phenomenon that also shows up in many other contexts.
In this segment, we consider the sum of independent Poisson random variables, and we establish a remarkable fact, namely that the sum is also Poisson. This is a fact that we can establish by using the convolution formula. The PMF of the sum of independent random variables is the convolution of their PMFs. So we can take two Poisson PMFs, convolve them, carry out the algebra, and find out that in the end you obtain again a Poisson PMF. However, such a derivation is completely unintuitive and does not give you any insight. Instead, we will derive this fact by using our intuition about what Poisson random variables really represent. We will work with a Poisson process of rate lambda equal to 1. But let us remind ourselves of the general Poisson PMF if we have a more general rate lambda. This is the PMF of the number of arrivals in a Poisson process with rate lambda during a time interval of length tau. And this Poisson PMF has a mean equal to lambda tau, and you can think of lambda tau as being the parameter of this Poisson PMF, so we say that this is a Poisson PMF with parameter equal to lambda times tau. Now, let us consider two consecutive time intervals in this process that have length mu and nu. And let us consider the numbers of arrivals during each one of these intervals. So we have m arrivals here and n arrivals there. Of course, m and n are random variables. What kind of random variables are they? Well, the number of arrivals in a Poisson process of rate 1 over a period of duration mu is going to have a Poisson PMF in which lambda is 1, tau, the time interval, is equal to mu. So it's going to be a Poisson random variable with parameter or mean equal to mu. Similarly, for n, it's going to be a Poisson random variable with parameter equal to nu. Are these two random variables independent? Of course they are. In a Poisson process, the numbers of arrivals in disjoint time intervals are independent random variables. What kind of random variable is their sum? Their sum is the total number of arrivals during an interval of length mu plus nu. And therefore, this is a Poisson random variable with mean equal to mu plus nu. So what do we have here? We have the sum of two independent Poisson random variables, and that sum turns out also to be a Poisson random variable. More generally, if somebody gives you two independent Poisson random variables, you can always think of them as representing numbers of arrivals in disjoint time intervals, and therefore, by following this argument, their sum is going to be a Poisson random variable. And this is the conclusion that we wanted to establish. It's a remarkable fact. It's similar to the fact that we had established for normal random variables. The sum of independent normal random variables is also normal. So Poisson and normal distributions are special in this respect. This is a property that most other distributions do not have, with very few exceptions. We will now study what happens when we merge independent Poisson processes. The story, as well as the final conclusion, is going to be similar to what happened for the case where we merge independent Bernoulli processes. In particular, we will see that the merged process will also be Poisson. What is the story? Suppose that you have two light bulbs. One of them is red and flashes at random times that are described according to a Poisson process with a certain rate, lambda 1. The other light bulb is green, flashes also as a Poisson process with a certain rate. Furthermore, we assume that the two light bulbs are independent of each other. If you are colorblind, so that the only thing that you see is flashes, but without being able to tell the color, what kind of process are you going to see? Well, you will see a Poisson process also, and at this point you can probably guess what the arrival rate is going to be for this Poisson process. It should be the sum of these two arrival rates of the processes that you started with. So this will be our final conclusion, but we want to verify that this is indeed the correct conclusion. So let us look at the situation in some more detail. We have the two processes, two arrival processes, the red one and the green one, and the merged process is formed by recording an arrival at any time where either of the two processes that you started with records an arrival. Let us now look at the time interval and think about the number of arrivals in the merged process during this time interval. What is that number? That number is equal to the number of arrivals that you have in the first process plus the number of arrivals that you have in the second process. Let's call those numbers n1 and n2, so that what we have here is n1 plus n2. Now, n1 is a Poisson random variable because this is a Poisson process. Similarly, n2 is a Poisson random variable. We assume that these two processes are independent. Therefore, n1 plus n2 is the sum of independent Poisson random variables, and therefore n1 plus n2 is also a Poisson random variable. This is reassuring. It's a good piece of evidence that the blue process is a Poisson process. But this is not enough. To argue that it is a Poisson process, we need to check the defining properties of a Poisson process. One defining property is the independence property. If we take disjoint intervals, the number of arrivals here is independent, or should be independent, from the number of arrivals there. The argument here is exactly the same as for the Bernoulli case, so we will not go through it in any detail. We just notice that whatever happens during that time has to do with whatever happens during those times in the two processes that we started with, and similarly what happens in these times has to do with what happens in these two processes during those times, because for each one of the two processes that we start with, we have the Poisson assumption, so that this interval is independent from that interval in the sense that arrivals here and arrivals there are independent. So because of this, whatever happens during those times has nothing to do with whatever happens in those times. So number of arrivals here is independent from the number of arrivals there. The other property that we need to check is that the probability of recording an arrival during a small time interval of length delta, that this probability has the right scaling properties, that it is linear in delta, in the length of this interval, and that the probability of two or more arrivals here is negligible. To see what happens during a typical interval on the merged process, we need to consider what is going to happen during that typical interval in the other two processes, and consider all the possible combinations. During a little interval, the red process is going to have 0 arrivals with this probability, 1 arrival with this probability, and 2 or more arrivals with this probability, which is negligible. Actually, here we're ignoring terms of order delta squared. These are the correct expressions if we only focus on terms that are either constant or linear in delta. We are ignoring terms that are of order delta square or higher. And similarly, for the green process, we have these probabilities for the number of arrivals that may happen during a small interval. For the merged process, we will have 0 arrivals if and only if we have 0 arrivals in the red process and 0 arrivals in the green process. The probability of these two events happening, because we assume that the two processes that we started with are independent, is going to be the product of the probabilities of 0 arrivals in one process times 0 arrivals in the other process. We multiply those two terms, and if we throw away the term delta squared, which is negligible, we see that this event is going to happen with probability 1 minus lambda 1 plus lambda 2 times delta. What's the probability that we get one arrival? This is an event that can happen in two ways. We could have one arrival in the red process and 0 arrivals in the green process, and this combination happens with this probability. Alternatively, we could have one arrival in the green process and 0 arrivals in the red process. This is this event, and it happens with this probability. Having one arrival in the blue process can happen either this way or that way, so the probability of one arrival will be the sum of these two probabilities, and if we throw away terms that are order of delta squared, what we're left with is just lambda 1 plus lambda 2 times delta. Finally, there's the possibility that the blue process is going to have 2 or more arrivals. This happens if we have one red and one green arrival, which happens with this probability, or if any one of the processes has 2 or more arrivals, which would be terms here, here, and these would be the scenarios. But we notice that each one of these scenarios has probability that's order of delta squared. This term also has probability of order delta squared. So overall, the possibility that the blue process has 2 or more arrivals, this is something that has probability that's of order delta squared. So during a typical small interval, there is probability proportional to the length of the interval of having one arrival, and lambda 1 plus lambda 2 is the factor of this proportionality, and the remaining probability is assigned to the event that there are 0 arrivals. There is essentially negligible probability of having 2 or more arrivals. But this, together with the independence assumption, is exactly what comes in the definition of a Poisson process with an arrival rate equal to this number. And so we have established that the merged process is a Poisson process whose rate is the sum of the rates of the processes that we started from. As before, we have a red Poisson process and a green Poisson process. We merge these two processes and we only observe the merged process. Here's an interesting question. This is an arrival of the merged process. Where did it come from? Is it red or is it green? We cannot know, but can we tell what is the probability that it came from the red stream? The way to answer this question is to look at the table of all the things that can happen during a little interval around that particular time in which we've had an arrival. We are told that there was an arrival at time t, or an arrival during an interval, a small interval around time t. This means that we are told that this event here has happened. Given this information, what is the conditional probability that actually this event here occurred? This is just the fraction of this probability divided by the total probability of the conditioning event. So the answer is lambda 1 divided by lambda 1 plus lambda 2. Does this answer make sense? Well, suppose that lambda 1 and lambda 2 were equal. In that case, by symmetry, when an arrival comes, it should be equally likely to have come either from the red or from the green stream, and this is consistent with this answer. We can reason similarly for a slightly different question. You wait until the kth arrival, let's say the third arrival. Where did that arrival come from? Well, that kth arrival occurred during a specific little time interval, and conditioning on it having occurred during that particular time interval, we can then repeat the reasoning that we had here and argue that given that we had an arrival, it just happens to be the third arrival during that time interval, there's going to be this particular conditional probability that it came from the red stream. So we obtained the same answer once more. Now, this arrival came from one of the two streams with some probabilities. This arrival came from one of the two streams with some probabilities. Does the origin of this arrival affect or depend on the origin of that arrival? Because we have assumed independence across time for each one of the processes that we started with, and therefore we also have the same thing for the merged process, whatever has to do with events during this interval is independent from anything that has to do with events in that interval. And because of this, one can argue formally, but hopefully this is intuitive enough, that the origin of this arrival and the origin of that arrival are independent events. And now that we have this property, we can answer questions such as the following. We've had 10 arrivals so far. What is the probability that exactly 4 out of these 10 are red? Each one of those arrivals has this probability of being red. The origin of different arrivals are independent of each other, so essentially we're dealing with 10 Bernoulli trials, each of which has two possible outcomes, red or green, and is red with this particular probability. Therefore, the answer is going to be given by the binomial probabilities, which is the probability of having 4 successes in 10 trials, and we obtain lambda 1 over lambda 1 plus lambda 2. That's the probability of a red to the number of red arrivals, and then the remaining probability 1 minus that, which is lambda 2 over lambda 1 plus lambda 2 to the remaining power, which is equal to 6. So to summarize, each one of the arrivals in the merged process has a certain probability of being a red arrival or a green arrival. Which one of the two is the case? We can think of it as an outcome of a Bernoulli trial, and the Bernoulli trials associated with different arrivals are independent of each other as a consequence of the independence of Poisson processes across time. We will now go through a beautiful example in which we approach the same question in a number of different ways and see that by reasoning based on the intuitive properties of a Poisson process, we can arrive quickly to the right answer. The problem is as follows. We have 3 light bulbs, and each light bulb is being lit at time 0. It starts working, and the light bulb lasts for a certain amount of time, which is random. So this light bulb lasts so long, this one lasts so long, this one lasts that long. The lifetime of a light bulb, the time until it burns out, will be a random variable. And we make the following assumptions. The lifetimes of the three light bulbs, which we denote by x, y, and z, will be independent random variables, each of which is an exponential random variable with a parameter lambda. We're interested in the question of calculating the expected time until a light bulb burns out for the first time. So in this picture, the light bulb that burned out first is this second light bulb, and this quantity is the time until the first burnout. How do we calculate this quantity? The time until the first light bulb burns out is the minimum of the times at which each one of them burns out. So we're interested in the expected value of this quantity. It's a random variable which is a function of three random variables. How do we calculate the expected value of a function of random variables? We can use the expected value rule. Let us take the function of interest, which is the minimum of three numbers. Then we need to multiply by the joint PDF of these three random variables, x, y, and z. Now, because these three random variables are independent, the joint PDF is the product of their individual PDFs, which are all exponential. And so we obtain this expression for the joint PDF. And we need to integrate this over all x, y's, and z's. So it's going to be an integral that goes for each one of the three variables from 0 to infinity. And here we have dx, dy, dz. So this is one approach that can give us the answer if you're able to manipulate and keep track of everything that happens in this three-dimensional integral. But this is too tedious, and this is not a good way to go. Let us try to think of an alternative way. Can we figure out the distribution of this random variable? It's a function of three random variables, so in some sense it's a derived distribution problem. So we can try to calculate the cumulative distribution function of the minimum of the three. So for the cumulative, we would be looking at the probability that the minimum of these three random variables is less than or equal to a certain number. It turns out that the calculations are a little faster if we look at the probability that this is larger than or equal to a certain number. What is this event? The minimum is larger than or equal to t if, and only if, all three of them are larger than or equal to t. So the probability of this event is the same as the probability that x is larger than or equal to t, y larger than or equal to t, and z larger than or equal to t. But now x, y, and z are independent, so we need to multiply the probability that x is larger than or equal to t, which for an exponential random variable is e to the minus lambda t, then the probability of the second event, which is again e to the minus lambda t, and finally the probability of the third event, which is again e to the minus lambda t, which is e to the minus 3 lambda t. Now we look at this expression for the probability that our random variable is larger than or equal to t and recognize that this is the expression that we have when we have an exponential random variable with parameter equal to 3 lambda. If you want to do it formally, subtract this quantity from 1 to find the CDF, take the derivative, and you will find an exponential PDF. So the conclusion is that this random variable is exponential with parameter 3 lambda. And since it's an exponential with parameter 3 lambda, then we know what the expected value is. It is going to be 1 over 3 lambda, and this is the answer to the question that you were interested in. Now, the fact that this is an exponential random variable, but with a different parameter, is a pretty clean fact, and so it should have a good explanation. Let us now try to think about a good explanation for this fact. Whenever we deal with an exponential random variable, one way of thinking about it is that this exponential random variable is the first time in a Poisson process. So imagine that there is a Poisson process that runs forever, and x is the first arrival time. For this light bulb, we can think the same way And since x and y are assumed to be independent, we can assume that here we have an independent Poisson process, independent from the first one. It has its own arrival times, and y is the first arrival time in this Poisson process. And finally, we have a third independent Poisson process, and the random variable z is the first arrival time in that Poisson process. So x, y, and z are interpreted as first arrivals in three independent Poisson processes. Now let us take these three Poisson processes and merge them. If we merge these three processes, what we obtain is a merged process which is Poisson with parameter equal to the sum of the rates or parameters of each one of the processes. So it's a Poisson process with parameter 3 lambda. Now, how can we interpret the random variable of interest, the first burnout time, in terms of the merged process? So the merged process has an arrival whenever one of those three processes has an arrival. The first arrival in the merged process will happen the first time that one of these three processes is going to have an arrival. Therefore, we can interpret the random variable of interest, the first burnout time, as the first arrival time in a merged process. But now the merged process is Poisson with parameter 3 lambda. Therefore, this random variable is going to be an exponential random variable with parameter 3 lambda. And from this, we also obtain the expected value of that random variable. The beauty of this last approach for coming up with the answer by reasoning in terms of merged Poisson processes is that we didn't have to do any calculations at all. Just use the intuitive understanding of Poisson processes and especially the interpretation of an exponential random variable as the first arrival time in a Poisson process. Let us now try to solve a somewhat harder problem. Let us try to calculate the expected time until all light bulbs burn out. So, one light bulb will burn out, then another one will burn out, and finally the third one will burn out. We want to find the expected time until this happens. Once more, we will be thinking of these burnout times as the first arrival times in Poisson processes. The total time until the third burnout can be split into different periods. There's a time until one light bulb burns out. And the expected value of this period here is going to be 1 over 3 lambda. What happens at this time? The second light bulb has burned out, so we can forget about it. Take it out of the picture. We have two light bulbs. Let us look at the time it will take until one of these two light bulbs burns out. So we're interested in this period of time. Now, the Poisson process starts fresh at this time. After this time, whatever happens is just an ordinary Poisson process as if it was starting at this time. So this is going to be an exponential random variable starting from this time, and this is going to be another exponential random variable. So the time until the next light bulb burns out, in this case, is going to be the minimum of two exponential random variables. We can think again about merging these two Poisson processes to obtain a Poisson process with total rate 2 lambda, and the time until one of these two burns out is going to be the first arrival time in that merged process, and so the expected time until the first arrival of the merged process is going to be 1 over 2 lambda. And finally, once this burned out has happened, we can forget about this light bulb. We're left just with one light bulb, and starting from here, we wait until that light bulb burns out. Once more, because of the fresh start property of the Poisson process, starting from here until it burns out is going to be a random variable, which is an exponential random variable, and in this case, an exponential random variable with rate just lambda. And by adding these three quantities, we get the expected time until all three have burned out. This is a problem that would have been quite hard to solve in a more analytical way. We're dealing with a random variable which is now the maximum of x, y, and z, and the distribution of this random variable is not so simple to write down, so that would not be a very good approach for going about this problem. But we managed to find the expected value of this random variable without having to write down its distribution by breaking this random variable into a sum of three particular random variables, each of which had a nice intuitive interpretation, and that was the key to the solution of this problem. In this segment, we discuss splitting a Poisson process into two different streams. So we have a Poisson process with some arrival rate lambda, and whenever there is an arrival, we decide to send it either to one or another stream. And for example, this arrival might be sent to that stream, this arrival might be sent to this stream, this arrival might be sent to this stream, that arrival might be sent to that stream. How do we decide where to send these arrivals? We make those decisions using independent coin flips of a coin that has a certain fixed bias equal to Q. So when this arrival comes, there's probability Q that it will be sent that direction, or probability 1 minus Q that it will be sent in the other direction. All of these coin flips are independent. So the decision on where to send the second arrival is going to be independent from the decision of where to send the first arrival. And furthermore, we make one more assumption, that these coin flips are independent from everything else. They're independent from the time history of the original Poisson process. For example, the coin flip that decides the destination of this first arrival cannot depend on how long it took for this arrival to occur. We will argue now that this stream is a Poisson process, and by symmetry, therefore, this stream is also a Poisson process. We need to verify two assumptions. One has to do with independence. The argument here is entirely analogous to arguments that we have already carried out in the past. Namely, disjoint time intervals in the original process are independent. Coin flips that happen during those disjoint time intervals are also independent of each other. And for this reason, whatever happens during disjoint time intervals in that stream will also be independent. The other property that we need to verify has to do with probabilities of small intervals. If we take a little interval here of length delta, what is going to happen during that interval? Well, we look at what happens during the corresponding interval in the original stream. In the original stream, the probability of having two or more arrivals, this probability is order of delta squared. So there's no way of having two or more arrivals during that little interval, or to be more precise, the probability of two or more arrivals here is going to be negligible, order of delta squared. What is the probability of having one arrival during that little interval? We will have one arrival here if we've had one arrival in this time interval, which happens with probability lambda times delta, and also the coin flip sent the arrival in this direction, which is something that happens with probability Q. And the remaining probability is assigned to the event of having zero arrivals during that interval. So the probability of two or more arrivals is negligible, and the probability of one arrival is proportional to delta, and that's what we need in order to have a Poisson process. The factor of proportionality that multiplies delta is equal to lambda times Q. Therefore, this is a Poisson process with parameter or arrival rate equal to lambda times Q. And by a similar argument, this process here is going to be a Poisson process with parameter equal to lambda times 1 minus Q. So, by splitting a Poisson process using independent coin flips, we obtain two different Poisson streams. Are these Poisson streams independent? For the case of the Bernoulli process, we had seen that the resulting streams were not independent. The reason for the Bernoulli process was that if I tell you that at a certain slot we had an arrival in this stream, that would tell you that in the corresponding time slot of the other process you could not have an arrival. And that was a source of dependence. It turns out that for the Poisson process, because it runs in continuous time, telling you that we had an arrival at this particular time instant does not give you any substantial or any non-trivial information about the other process, and the two processes remain independent. This result is surprising in some ways, but it is true. A mathematical derivation proceeds along a line that's a little different from the intuitive argument that I just outlined, and we will not go through that derivation, but it's a useful fact to know. In this segment, we discussed the so-called random incidence paradox for the Poisson process. It's a paradox because it involves a somewhat counterintuitive phenomenon. However, we will understand exactly what's going on, and in the end, it will cease to be a paradox, and we will have an intuitive understanding of what exactly is happening. So consider a Poisson process that has been running forever, or think of it as a Poisson process that started a very long time back in the past. To make things concrete, suppose that the arrival rate is 4 arrivals per hour, so that the expected inter-arrival time is 1/4 in hours, or that would be the same as 15 minutes. For example, suppose that the bus company in your town claims that buses arrive to your stop according to a Poisson process with this particular rate. But you don't really believe that your bus company is telling the truth, and you decide to investigate. So what you do is the following. You show up at some time at your bus stop and wait until the next arrival comes, and also ask someone who lives near the bus stop what time was the last arrival, and they tell you the last arrival happened at that time instant. And you measure this amount of time, which is the inter-arrival time, record what it is, repeat this experiment on many days, and calculate an average. What you're likely to see turns out to be something around 30 minutes. At this point, you could go to the bus company and challenge them. You claim an arrival rate of 4 arrivals per hour, which would translate into inter-arrivals of 15 minutes, but every day I go and check the inter-arrival time and I find that they're close to 30 minutes. What's the explanation? What's going on? Is it that the belief or the claim of the bus company is incorrect, or is there something more complicated? So let us try to understand what's going on by being very precise and careful. You show up at the bus station at some time. Let's call that time T star. You ask someone who has been at the station when was the last arrival time, and they tell you, and it is some number u. You wait until the next bus, and the next bus arrives at some future time, capital V. You are interested in the inter-arrival time that you are observing, which is the difference between those two random variables, v minus u. Now this difference, let us split it into two pieces. There's one piece from t star until v, which is v minus t star, and there's another piece, which is the first interval, and this is t star minus u. Now t star, the time at which you arrive, is just a constant. Suppose that you arrive at the bus station at exactly 12 noon. There's nothing random about it. However, v and u are random variables. What kind of random variable is this? You show up at 12 noon and you wait until the first arrival. Because a Poisson process starts fresh at any given time, so after 12 noon it starts fresh. This is the time until the first arrival in a Poisson process with rate lambda. So this is a random variable which is exponential with parameter lambda. Now let us understand what this random variable is. One way of thinking about it is to think of the Poisson process running backwards in time. So you live time backwards. You show up at 12 noon and then time runs backwards and you wait until you see a first arrival coming in this backwards universe. So we're dealing here with the time until an arrival in a Poisson process that runs backwards in time. What kind of process is a backwards Poisson process? If you take a Poisson process and reverse time, the independence assumption is not affected. Disjoint time intervals are independent. Even if you reverse time, disjoint time intervals still remain independent. Any given time interval of small length delta will have certain probabilities of an arrival or of two arrivals, and these will be the same whether time goes forward or time goes backward. So the conclusion from this discussion is that the backwards running Poisson process is also a Poisson process, and so this time until the first arrival in the backwards process is just like the time until the first arrival in a Poisson process, so this also is an exponential random variable with parameter lambda. Even more than that, these two random variables are independent of each other. Why are they independent? The length of this time interval has to do with the history of the Poisson process after time t star. The length of this time interval has to do with the history of the Poisson process before time t star. But in the Poisson process, because of the independence property, the past and the future are independent, and therefore this random variable is independent from that random variable. In any case, the expected value of the interarrival interval that you see, the expected value of this random variable, is going to be the expected value of one exponential, which is 1 over lambda, plus the expected value of another exponential, which is 1 over lambda, and we get a result of 2 over lambda. And that's why, when you actually carried out the experiment, you saw interarrival intervals that had a length of 30 minutes as opposed to the 15 minutes that you were expecting in the first place. Now, how can this be? Since the interarrival times in a Poisson process have expected value 1 over lambda, how can it be that the expected length of the interarrival times that you see have an expected value of 2 over lambda? Well, the resolution of this paradox has to do by what exactly we mean when we use the words an interarrival time. There's one interpretation, which is the first interarrival time, the second one, the 100th interarrival time. Each one of these actually has an expected value of 1 over lambda. But this is a different kind of interarrival time. It's not the first or the second or some specific kth interarrival time. It's the interarrival time that you selected to watch. When you show up at a certain time, like 12 noon, you're more likely to fall inside a large interarrival interval rather than a smaller interarrival interval. So just the fact that you're showing up at a certain time that's uncoordinated with the rest of the process makes you more likely to be biased towards longer rather than shorter intervals, and this bias is what causes this factor of 2. So it's an issue really about how you sample or how you choose the interarrival time that you're going to watch. And this particular sampling method has a bias towards longer intervals. As we will see, this is not something that's specific to the Poisson process. In general, in many occasions, there are different ways of sampling which give you different answers, and we will go through a number of examples that will give you some intuition about the source of the discrepancy between these two answers. In this segment, we go through another random incidence example, one that does not involve a Poisson process, but a much simpler arrival process. We do this for two reasons. One is because of the simplicity of the example, perhaps the intuition will be a little more transparent, and the second reason is to illustrate that we're dealing with a phenomenon that's not specific to the Poisson process, but is much more general. The example is as follows. We have an arrival process in which arrivals happen at random, and the consecutive inter-arrival times are independent, identically distributed random variables. However, unlike the Poisson process, these inter-arrival times are not exponential random variables, but instead we assume that they're either 5 or 10 minutes with equal probability. So we have an arrival, the next arrival may happen 5 minutes later, the next arrival may again happen 5 minutes later, then maybe we get an inter-arrival interval of length 10, then maybe another inter-arrival interval of length 10, followed by one of 5, and so on. What is the expected value of the kth inter-arrival time? Well, an inter-arrival time is with probability 1/2 of length 5 and with probability 1/2 of length 10. So the average inter-arrival time is 7.5. Now you show up at a random time. And by random we mean a time that's completely uncoordinated with the arrival process. You show up at some point in time and you look at the inter-arrival interval in which you fall, and you're interested in the length of that particular inter-arrival interval. What is the probability that you fall inside a 5-minute inter-arrival interval? Since intervals of length 5 are as likely as intervals of length 10, in the long run there is going to be roughly as many 5-minute intervals as there will be 10-minute intervals. On the other hand, the 10-minute intervals occupy twice as much space on the real line. And for this reason, it is 2 times more likely that you will fall in a 10-minute interval rather than a 5-minute interval. In other words, the probability of falling in a 5-minute interval is going to be 1/3, whereas the probability of falling in a 10-minute interval is going to be 2/3. For this reason, the expected length of the inter-arrival interval that you get to see when you arrive is equal to, with probability 1/3 you see a 5, and with probability 2/3 you see a 10, and this number evaluates approximately to 8.3, which is indeed larger than 7.5. The conclusion from this example is similar to the one that we had for the Poisson process. Although the average inter-arrival time is 7.5, when you show up at a random time, you're more likely to fall in a larger interval, and for that reason, on the average, you will be seeing longer inter-arrival intervals. The calculations that we carried through in that simple example can be generalized for more general arrival processes called renewal processes. In a renewal process, once more, the consecutive inter-arrival times are independent, identically distributed random variables, but they have a general distribution. For this case, there's a formula again that tells us the length or the expected length of the inter-arrival interval that you get to see. But the main message from this example is that it does make a difference how you sample, how you choose what to watch and what to measure. It makes a difference whether you decide to measure the kth inter-arrival time and its average value, or to decide to measure an inter-arrival time that's chosen by showing up at a random time. The two methods of sampling give you different results, and we will see next a few examples that have this particular flavor. In this segment, we want to reinforce the message that how you choose to sample can give different results, and the choice of sampling is important. Suppose you're interested in measuring the average family size in some population. Suppose that there are families that are small and have just one person in them, and there's also a family that has many people in it. What does it mean to measure the average family size? One possibility is to pick at random a family, each family being chosen with equal probability, and talk about the expected value that you get, or the average value if you sample that way. In this particular example, with probability 1/4 you get a 1, with probability 1/4 you get a 1, with probability 1/4 you get a 1. So the answer would be with probability 3/4 you get a 1, and with probability 1/4 you get a 6. But suppose that instead you pick a person at random and you ask that person, how big is your family? What's the expected value of the answer you are going to get? Here we have 9 people. Out of those 9 people, 3 of them will give you an answer, my family has size 1, and 6 of those people will give you an answer, my family has a size of 6, and this number is going to be larger than the previous number. You're going to get different answers. So it is possible to have a situation where you can make a statement such as the following. The average family size is 3, but the average person lives in a family of size 4. There is no contradiction between these two statements because we're measuring different things. Another example of the same flavor. You're interested in the average bus occupancy. You're interested in whether buses are crowded or not in your city. One way of carrying out this calculation is to pick buses at random. Each bus is equally likely to be picked, and see how many people are riding this bus. Another possibility is to take a typical passenger, a random passenger, and ask them, how crowded was your bus? Take an extreme case. Suppose that half of the buses have 0 people in them and half of the buses have 50 people in them. If you look at random buses, then the average occupancy would be 25. But if you ask passengers, all of the passengers would report 50, and it would be again a different answer. A similar situation is if you're talking about average class sizes. One method is to look at all the classes, see how many students there are in each class, and take the average. Another method would be to ask a typical student, how large is your class? Because more students are in large classes, when you pick a student at random, you are likely to get a higher answer as opposed to when you look at a random class. The moral from all these examples is that it is very important to be careful about what you choose to sample. When you pick at random, what exactly are you picking at random? And you need to be aware that different sampling methods measure different things and will generally give you different results.